class. Today's lesson is on gravitational field. This is class by Raj, teaching for Physics Form 6, Semester 1. The learning outcome for today's lesson is class to explain the meaning of gravitational field, to define gravitational field strength as a force of gravity per unit mass, and to define and use the equation for gravitational field. What is a gravitational field? A gravitational field is a region where gravitational force acts on a massive body. The gravitational field is illustrated by the line of forces. Line of forces. The direction of the gravitational field is towards the center of the Earth. The quantity that used to measure how strong is the field is called as a gravitational field strength. Gravitational field strength is a vector quantity. Therefore, it has a magnitude and direction. Our first concept for today is to define the gravitational field strength. The gravitational field strength at a point in a gravitational field is defined as the force of gravity per unit mass at that point. Gravitational field is a region, is a region where if any object enters into the region, a gravitational force will act on the object. So what is a gravitational field? It's a region where a gravitational force acts on massive bodies. So in case if there is an object enters into the region, then what will happen? A gravitational force will act on the object. So say for example, this is a gravitational field of the Earth. So this is Earth and this is the gravitational field of the Earth. And the strength of the gravitational field, that means how strong is the field. The quantity is called as a gravitational field strength. It's called as gravitational field strength. So gravitational field strength, symbol is capital E, is what? Is how strong is the gravitational field. Is how strong. It's a measurement of how strong is the gravitational field at a particular point. So the direction of the gravitational field will follow the direction of the gravitational force, which is towards the center. So here if you see here, gravitational field at a point. Now let's choose a point here. And at this particular point, say for example we put a point P here. Point P. There is a mass M. So I'm going to put here point P. There is a mass M. So the gravitational field strength at a point. So what is it? So you see class, the concept says when a mass enter into the gravitational field, the mass will be exerted by a force. The mass will be exerted by what? By a force. Now this force is called as a gravitational force. It's called as what? It's called as a gravitational force. So now when this mass has entered into the field, the mass will be exerted by a force which is the gravitational force, which is towards the center of the earth. Okay, so the gravitational field strength at that particular point, the gravitational field strength at that particular point in a gravitational field is defined as the force of gravity, E, as the force of gravity, which is F over M. Okay, and gravitational field strength is a vector quantity. It is a vector quantity okay, which has a direction and the magnitude. Okay, and the unit for gravitational field strength, it can be Newton per kg. We take unit from the formula, yeah, Newton per kg, or we can say ms negative 2. Okay, so that is the first concept. A first concept is to define what is a gravitational field strength. Okay, so again, a gravitational field strength at a point in a gravitational field is defined as the force of gravity per unit mass at that point. Okay, all right. Concept number 2. In this concept, we will look at the relationship between the gravitational field strength and the acceleration due to gravity. The gravitational field strength, which is E, at a point in a gravitational field is equal to the acceleration due to gravity at the point. Concept is, the first concept is on the first concept we learned just now is the definition of the gravitational field strength. The next concept says that the gravitational field strength at that point, the E at that point, equals to the acceleration due to gravity at that point. Okay, so I'm going to write here in words, gravitational field strength at that point equals to the acceleration due to gravity at that point. Okay, so the E at that point is equals to the G at that point, the next concept. Okay, and since the E at that point is equals to F over M, so therefore we can also symbol the gravitational field strength, we can symbol the gravitational field strength as the symbol G equals to F over M. Okay, it's the same symbol is used. So if you look and you turn to page 133 in your textbook Oxford Fajar, you realize that in your Oxford Fajar, the gravitational field strength is symboled as small g. Okay, why? Because you see here also is symbol as small g. Why? Because it says in the concept here, the gravitational field strength at a point equals the acceleration due to gravity at that point. So E is equals to G. So hence the symbol G is used for gravitational field strength. Okay, alright, so because they are similar values, so they use the same symbol. Okay, so that is the next concept. The next concept is the weight of the body is the gravitational force on the body. So when we talk about the weight of the body, which is W, equals to mg. Is the gravitational force on the body. So gravitational force is capital F. So the concept says that W is equals to F and W is mg. Next one is assuming there is another point here. We're going to choose a point here. Okay. In this particular point, which I'm going to also put point, maybe point Q. In this particular point, there is a small mass m which enters into the gravitational field of the earth. Enters into the gravitational field of the earth, which is the region. Where anything enters into the region, there will be a force exerted on that mass or on that thing. Okay, so what happened is, once when the mass enters into the gravitational field of the earth, what will happen? The first thing, a force, which I'm going to explain here, a force will be exerted on the mass. A force will be exerted on the mass. Okay, so this force will be directed towards in this direction, which is F. Okay, which this force is called as the gravitational force. Okay, and this gravitational force which we have studied, the formula will be F is equals to Gmm over R square, where R is the distance from the mass to the center of the earth. Okay, so R is the distance from the mass to the center of the earth, which is R. Okay, so here if you realize here that I didn't put the negative because I'm emphasizing on the formula. But if you want to put the negative, you can put the negative to indicate the direction of the force is decreasing R, is opposite to the is opposite to the increasing R. Okay, the direction of the force is opposite to the increasing of R. Okay, alright, so then what will happen is that the gravitational field strength at that point, okay, the gravitational field strength at that point, which I'm going to use another color here, the E at that point, which is equals to the G at that point. So I can say that the gravitational field at that point is the F, okay, is the F divided by the mass at that particular point. Okay, so therefore the gravitational field strength G is equals to negative Gmm over R square divided by M. So you get G equals to negative Gm over R square. So from here you realize that the gravitational field strength G is inversely proportional to R square. If you want to put the negative also can, is inversely proportional to R square. Okay, so if you look at this before that, what does this negative means? The negative is to show the direction of the gravitational field strength is in the direction of decreasing R. In the direction of decreasing R, or we can say in the opposite direction of increasing R. Okay, that is towards the earth, or we can say the direction is towards the earth. Okay, alright, so if you look at your textbook, which is page 134, you turn to page at 134, you will notice this is a graph of what? Of gravitational field strength, with distance R from the center of the earth. So because there's a negative, so you will notice it's in the negative field, so you get the shape of the graph in such a way. So this graph is very, very important graph to bring into remembrance. Okay, so please remember about of this graph. Alright, okay. Concept is for R, which is same as the radius of the earth. Okay, so for our distance, okay, so this is the mass m. This is the mass m. Now the mass m is at the surface of the earth, okay, which is already enter, which is not to say enter, which is already inside the gravitational field of the earth. So you can visualize the gravitational field of the earth, which is something like this. Wait. Okay. Yeah, I'm just drawing partly because I just want you all to see that you can draw fully also, no problem. Okay. Alright, so this is the mass m, which is the gravitational field of the earth is towards the center. Okay, so the mass m is on the surface of the earth. So what happens? As usual, when the mass enters into the gravitational field of the earth, the mass will be exerted by a force. Okay, and it's a gravitational force where the force will be towards the center of the earth, which is F. Okay, so F is equals to Gmm over what? Capital R squared, because at the surface of the earth. Okay, alright, from here to here, R is equals to small r. Alright, then what will happen? Okay, this is concept number 1. Okay, concept number 2. The weight of the body is equals to the gravitational force on the body, which is W is equals to F. Okay. Alright. So the weight of the body is towards where? Where is the direction of the weight of the body? Okay, wait. Hold on. I'm looking for... Okay. So the weight of the body is in this direction, W. Okay, so the weight of the body is equals to the gravitational force on the body. So therefore, we solve this, we get W is equals to mg, m time acceleration due to gravity, F is equals to g m m over r square. So g is equals to g m over r square at the surface of the earth. Okay, so what are we supposed to take note of? Alright, we are supposed to take a note of that the G is directly proportional, inversely proportional to the radius square. Okay. Alright. Next concept, we are going to look at the variation of G, which is the acceleration due to gravity with distance r. So the first example will be r, which is greater than the capital R, which is the distance r, which is greater than the radius of the earth. Now we know that when there's a mass m here, okay, so I'm going to just put here, there's a mass m. Okay, now this mass m enters into the gravitational field of the earth. So you know, you can also draw to visualize the gravitational field of the earth, which is towards the center of the earth. Okay, so you realize that I'm drawing the gravitational field of the earth, which is towards the center of the earth. Okay, so it's something like that. Okay, so you can keep on drawing that to visualize and to understand how it works. Okay, and we know the direction of the gravitational field is towards the center of the earth. Okay, so just maybe we draw a bit more, then here a bit more. Okay, so what happens is now the mass m enters into the gravitational field of the earth. So when the mass m enter into the gravitational field of the earth, what happens, class? A gravitational force, first one, a gravitational force acts on the, a gravitational force acts on the mass, or is exerted on the mass. Okay, so the direction of the gravitational force, which will be in this direction, F, which is towards the center of the earth. Okay, all right. Of course, we also have a gravitational force here, F, yeah, but that one is under the concept of Newton's third law. So we're going to just focus on this first. Okay, a gravitational force acts on the mass. Okay, so what will happen? What will be the formula of the gravitational force? It will be F equals to I can put my negative, or I don't want to put also can, because the negative just speaks about the direction. So now we are just going to look at the magnitude. Okay, so I just look at F equals to G M. Okay, the mass of the earth is M, and then times with M according to the universal Newton law of gravitational, which is divided by the distance, which is R squared. Okay, all right, then B, the concept. Okay, the concept is, the next concept is, the weight of a body is the gravitational force on the body. Okay, the weight of a body is the gravitational force on the body. Okay, so first I'm going to just draw it here to highlight the concept. If you know the concept, you don't need to memorize how to derive the formula, class, because you understand how it works. Okay, so the weight of the body equals to the gravitational force on the body. So there is a weight here, which I'm going to take a green pen. Okay, so this is the weight of the body, which is W, is equals to the gravitational force on the body. So W is equals to F, and we know W is what? W is mg, and what is F? F is gmm over R squared. And then we get G equals to gm over R squared. So here we realize that okay, that the G is inversely proportional to R squared. This is what we realize. Okay, okay, so later when I teach about this, we will look at the concept here. Okay, so this one also important. All right, okay. So for R, which is greater than capital R, okay, the G is gm over R squared. The acceleration due to gravity is equals to gm over R squared, where G is inversely proportional to R squared. Let's look at the part where the mass is in a radius which is less than the distance of the earth. Okay, now we have earth. Okay, from the center of the earth to the surface of the earth, the radius is capital R. Okay, and then its mass is capital M. Okay, now we have a small mass M. Okay, a small mass M, which is inside the earth, which is in a distance of R, which is lesser than the radius of the earth. Okay, so the concept is the part of the earth that attracts the mass M. Okay, the part of the earth, the part of the earth, okay, the part of the earth that attracts the mass M. Is of radius R and mass m naught. Okay, so the part of the earth that attracts the mass m, okay, will be this part. Okay, will be this part of the earth. Okay, so will be this part. And the mass is m naught, radius is r. So based on the concept, it says that there's a gravitational force, okay, there is a gravitational force F, okay, and the gravitational force F equals to the weight of the body, okay, is equals to the weight of the body. So the gravitational force will be G m naught times with m over r square. Okay, all right, so you notice that I didn't put the negative here because I'm looking at the value of the magnitude. So the negative is just to show that it's an attractive force. Okay, and the W will be mg. Okay, and then therefore we cancel, we get G equals to G m naught over r square. Okay, now we want to substitute the value of m naught. So we know density for this part of the earth, okay, is equals to mass over volume. Okay, and mass is equals to volume times with density, where volume is 4 over 3 pi r cube times with density. So I take this, I substitute inside here, I get my G equals to G, small g equals to capital G with the gravitational constant times with m, 4 over 3 pi r cube rho divided by r square. Okay, so therefore if I cancel it, I get G 4 over 3 pi r rho. Okay, now if I make it and arrange it properly, I bring out the constant out from the formula. I get 4 over 3 G pi r rho. Okay, so rho usually we do it in a slanting point here. Okay, alright, so then we see from this relationship the G here at this particular point will be G equals to 4 over 3 pi r rho. Where we see the relationship of the G, we realize that the G is directly proportional to r. So we can conclude that G is directly proportional to r when r is lesser than capital R. Okay, all right. So we have already learned the three concepts. So let's just conclude all those three concepts. Okay, all right. So that is it for r, which is lesser, the radius which is lesser than the radius of the earth. Include the whole entire acceleration due to gravity with a distance r from the center of the earth. Okay, so we can divide it into three parts, which is, all right, which we have r, which is lesser than the radius of the earth. Okay, and we know at this point, at this distance here, we know that the acceleration due to gravity is directly proportional to the distance. Okay, so that is why we have a straight line here. Okay, we have a straight line here. Okay, so I'm going to just take a pink pen and I'm going to just draw a straight line here. Okay, for this. All right, so at the radius of the earth, which is capital R, we know that the G is equals to Gm over R square. So since G is inversely proportional to R square, so at this particular point, we know that the G is the highest value. Okay, the G is the highest value. The acceleration due to gravity is the highest value. Okay, then as the distance increases from the surface of the earth, as the distance increases from the surface of the earth, then we realize that the G decreases. Okay, so here is r which is lesser than the radius of the r which is greater than the radius of the earth. Then from the formula we realize that g, acceleration due to gravity, is inversely proportional to 1 over r square. So when r increases, g decreases. So that is the reason you have this line. Okay, all right, so that is the summary for today's lesson. Thank you, class. The acceleration due to gravity and the gravitational field strength on the surface of the earth is not the same. It is because the earth is not a perfect sphere and the rotation of the earth about its axis. Now, if you look at this class, you will realize that the radius of the earth at the equator, r1, is greater than the distance of the pole from the center of the earth, r2. So, r1 is greater than r2. And then we know that the acceleration due to gravity is inversely proportional to r square. So therefore, the g at the equator is less than the value of g at the pole. So therefore, we can say that the gp, which is the acceleration due to gravity at the pole, is greater than the acceleration due to gravity at the equator. The difference between the acceleration due to gravity at these 2 points will be GE equals to GP minus R omega square.